morning, everyone. Welcome to week 4, and today's lecture is optimization in neural networks. So, guys, what is optimization in neural network? Optimization in neural network is the process of adjusting model parameters like weights and biases to minimize the loss function and improve the model's performance. Having said that, meaning if I can adjust weights and biases in a way that my y predicted, which is the output, becomes equal to y, which is the input, I have minimized my loss function and my model is ready. So this is the principle of optimization, to somehow play with weights and biases to minimize the loss function such that your y hat becomes equals to y. Now, guys, what do we see all the time? Any AI code, if we start reading it, what are the main terms that comes? The main terms that will come is that we are creating a neural network and we have a model that is, we will see that there is a sequential model here. Then we will come across the terms like optimizer is equals to Adam. And that time you ask yourself, why I'm using Adam? Is there any other optimizer that I can use? And as a beginner, it's very tough to understand. Then we have loss functions such as binary cross entropy, or you can have a simple loss function such as mean absolute error or mean square error. And then also you ask which loss function to use. Then you have, metrics. In metrics also you have accuracy, precision, recall, and you want to, know what is the right metrics, to measure my model. So today, the lecture is about this. We will talk about, first of all, we'll do the reminder on what are neurons, and then I will provide you the introduction of activation function. And this basically is a summary from lecture 6, but it is very important for me to revise it here because everything is built upon that problem. And then we'll talk about types of activation function. After that, we'll talk about what are loss functions. And then we'll talk about what is gradient descent or backpropagation. Without a further ado, let's dive deep. Okay, guys, let us have a quick reminder on what are neurons and on the problem that we did in lecture 6. And then let's introduce activation function. Okay. Guys, what is a neuron? So in front of you, you have something called neural network, right? And inside the neural network, you have, of course, it is made up of several neurons, but let's understand step by step. So inside the neural network, you have input layer, and this is your input layer, where each of you have different independent features, 1, 2, 3, 4, and like this, you can have several independent features. And all these independent features, they are connected to your first layer, which is your hidden layer. This is your hidden layer. And all these, this is your hidden layer, first hidden layer. This is your input layer. And all these neurons, they are somehow connected. Let's look how. So guys, all these independent features, they are connected to neurons. So I am just choosing a different color. such that each of the independent feature is going inside each neuron. And it will give you some kind of, addition, that is y, which is that I told you last time, wxi plus b. And then the same thing, it will be your summation. Then the same thing is happening inside the neuron 2, where it is connected to all the input parameters. And now you will have something as a summation as y hat, which will be also equal to wixi plus bi. So guys, the difference in y and y hat is very little. They are very similar, but there are different slopes and weights that I talked about in the last class is there. And then the same thing is going inside, the same inputs are going inside the neuron 3, and it gives you the output y double hat. And this is also wixi plus bi. And similarly, in the neuron 4 and 5, you will have y hat and y. So what is the difference between all these different, y prime, y double prime? Now the difference is very subtle. And then all these y hats, they go to now second layer. And then the similar thing happens and a new weight is calculated. So you see, your model is so dense that, it is not stopping to learn, or it's not doing any compromise. And we have different neurons that do the same thing that each one of them are doing. And then finally, it is the final weights that is calculated from all these weights. So today, what we are going to revise is, we are going to basically talk about, this is my input layer. This is my hidden layer. In this model, I have 3 hidden layers, 1, 2, and 3. And then I have the output layer. And today, we'll do a reminder that how does this different input features or different independent features go inside one neuron, and then we'll quickly revise the mathematics that goes inside, and then we'll apply the activation function. So guys, now let us just zoom inside one neuron. So what is happening inside one neuron? So inside one neuron, guys, it is definitely connected to input parameters. Now, these input parameters are independent features. And here, definitely, we are doing something called spam and ham classification. But to make your life simple, in the lecture 6, I explained some very easy problem that your independent features were, we were doing a dementia prediction neural network model, and your input feature was age, diet, and exercise. And all these input features, they together are going inside one neuron. And we did, we dive deep that how inside the neuron this data is getting processed, what is the mathematics inside the neuron. And today we will go in detail that how are activation functions working. And finally, we had the output probability of dementia risk probability, right? Okay. Now, guys, let's quickly do a reminder on that problem. Now, we are predicting, we have 3 input parameters. One is your age, other is your exercise, and third is your junk food. And all these 3 parameters are contributing to dementia. And we have this data from the hospital. And what I did was, I just plotted, if this was my X, that was the age of the patient, Y, which is the probability of dementia. And I plotted on an Excel sheet where this is my Y, this is my X, and I got a relationship between Y and X. And that relationship comes from when I try to fit this equation by the equation of line, and this relationship was slope. And if you remember, from your school days that y is equals to mx plus c is the final equation of line, which can be applied to such scenarios where you see a linear relationship. Now, this slope here is m, and this is what is exactly happening inside the neuron, where you have this famous equation y is equals to wx plus b. So from this, we got a weight value, which is equals to 0.23. If you see that, this is y is equals to mx plus c. And finally, when I fit this mathematically, I get this equation 0.023 plus bias. Now, what is this bias, guys? This bias was the intercept that it is making here on this curve. This is your bias. So this is how inside a neuron the maths is operating. Between an independent feature, we have an independent feature that is giving you a relationship with the final output, and we get something as weight, and we get something as bias. And bias is very important because we are giving this kind of flexibility to your final, answer, because we want something here that LHS should be equals to RHS. For more details, please visit video 6. That is a lecture 6 from this bootcamp. Now, we understood from this curve that your final dementia, it depends on the age, and the weight that we have is 0.023. Okay. Now, we also had other two parameters. Now, other two parameters that we have is exercise days per month and dementia. Now, in the exercise days per month and dementia, I did exactly the same thing. I went on Excel sheet, I started plotting my Y versus X, and I got a relationship here. And this was my M, or I can also say this is my weight. The value is equals to minus 0.053, as you see on the screen here. This was the value. And I got this relationship by simply fitting the equation of line, right? And this is my intercept for this problem, which is 0.81. You can just see here. And this again tells me that how my output, the final dementia output, depends on the exercise. It depends, minus 0.053 is the proportionality that, this much exercise is contributing to your dementia. Now, what is happening here is the third independent parameter we had was junk food. I did the same thing. So how many independent parameters you will have? So guys, independent parameters in, this slope is all these, if you have a slope, y to x, x is your independent parameter. Now we did the same thing. As many independent parameters you will have, your final output will have certain relationship with that independent parameter, and that is weight. We did that. We got the value here as 0.047, right? And like this, I can have n independent parameters, and I will have a relationship of those independent parameters with my y output. Now here, this is very important, that all the problems on the deep learning can be divided, into this. Any problem that you think, that's why deep learning became so famous. Now, I talked about last lecture about the problem of housing. You can also talk about, any problem that, tomorrow it would rain or not. It will depend on several independent parameters. One parameter could be, which month it is. Second parameter could be, is it, which country is it? Am I talking about US or am I talking about Canada? Then you can talk about, what is the month, country. Then you can also talk about if there is any natural disaster coming here. So there is more probability of rain. And all these three parameters, they are not dependent on each other, right? They're independent parameters, and they independently influence finally your Y output, right? And that is what we have done here. And that is the idea behind deep learning, that you can break any problem into these independent parameters and can find the relationship. Well, this is a very good, background. Now we will quickly go towards the main topic, is activation functions, right? So guys, now what is happening? You have these three independent parameters: age, exercise, diet, and we are calculating that, what are the chances? I have age, 60, I exercise not a lot, and my diet is very bad. What are the chances that I'll have dementia? And this is what we are doing here. So from your main data on the age, we got this weightage of 0.023. With your main data on exercise, we got this weightage of 0.052. And your main weightage, you got as 0.047. All these things, they go and they add up inside the neuron. So inside the neuron, it is, that equation, if you remember, y is equals to mx plus c. Here, this is your y1 minus 0.053 into exercise. This is your y2, and this is your y3. And all these things together is contributing to y, which is kind of, output from the one neuron before activation function. Now, guys, we introduce something now. After this y is calculated, this output has to go through an activation function. Why this output has to go into activation function? Because all these age, exercise, and diet, they have different mathematical units. They will give you different, relationships with the slope. And you want to put it all together on one scale. And to do that, we pass this final value of y through something called activation function. Now, on your screen here, you have, z, that is something that is a sigmoid function, that your y, that was your final value. From here, it goes inside this here. And, for each case, now, you will have a different value that will contribute to your final y. Meaning that I bring 3 people in, and I have 3 data set in, and one will be, one person is here. This has age of 23. Exercise, he does once. Diet is very good, 2 times. And you can calculate now whether he will have dementia or not. So this is the final y of this person that I will put in, and I'll get one value out. Now, second person who goes in, let's draw the second person here. And I've just, given it a little tail. And this second person, he is, 26 years of age. He, has not also a good exercise, lazy guy. He has a diet that is, very, very, very poor. And, and he eats like 24 times, junk food. Now, this will also give you one other y. And like this, you will have several y's here. And then finally, you will be able to plot all these y on one curve, because sigmoid function is reducing all your data points into one scale. So that is the idea behind the activation function, that all the y that I will have finally from each data set, guys, this is on screen is data set 1, right? Where you have particular age and diet and exercise, for data set 1 coming from first person. Now I can also have the data set 2 coming from second person. And that will also, be giving me some y. And I'm able to plot those y together using a sigmoid function. And like this, I can have many y's. And I make a sigmoid function like this. So this is the idea behind the activation function. Now, so guys, this is something that, is the same thing, but now here we are clear. This is just a summary. We had, finally the equation of y, it looks to you like this, right? And this equation of y now, in the next case, this is equation of y, which is inside the neuron. Now, guys, as I told you, this is the final equation. And finally, I have here different, ages. One is 21, 20, 0. And I did the same thing, which I told you. I have this data case, and I tried to put in this equation here. That was my, equation that I had if I had these 3 independent parameters. And now in this equation, I try to plug in, 0.023, age is 21, exercise is 20, junk food is 0, right? And finally, I get my y is equals to minus 0.0288. And then I do the same thing on a guy with age 51, exercise 20, junk food 0. And I get, I plug into these equations here and in the same equation as above. And what I get here is, I get something called y is equals to 0.042. This guy's 0.028 comes as the addition of B1 plus B2 plus B3. Like this, I have several points, right? I have several points. I have a data sheet. And in the data sheet, I have this data. And this is, you can right now consider it as the test data. It's coming out. And I am trying to plot it. Now, idea is that this y, I'm trying to plot it on a sigmoid, or I have converted this each y, that is z is equal to sigmoid y. And this z is equals to sigmoid y, that means I have just applied this function. It is given to me as 0.428, 0.59 for the second person, third person 0.468, for the fourth person 0.586, then for the fifth person 0.485. And now I have plotted them inside a Excel sheet. And because I use the sigmoid function, it will have a shape like this. Sigmoid function has a S shape. I will also go into the next slide on a little bit more detail. So I just plotted this. And this is my final, plot of y coming out. And this happens in the output layer, guys. In the output layer, I generally use a sigmoid function. Whenever it is a binary classification task, that's what I want to do. Because now, if I plot all these points, all the sigmoid points here, now I will plot it. And now after plotting it, for example, let me change color. This was my person 1. This was, you can say this was my person 1. This was my person, 2. This was my person, 3. This was my person, 4. This was my person 5. And this is how all the results can be plotted, and they will follow this trend because I have applied a sigmoid function. And now I apply a threshold value here. This was my y. And this I apply a threshold of 0.5. And I talk about that above 0.5, whatever my value comes, I will say that these people, will have dementia, yes. Because you see here, all of this probability was 1, yes. And then here, people will have no dementia, y is equals to 0. So this is what is happening inside the neuron. We have independent parameters that are calculating, your y is equals to mx plus c. By that we get, your weights, and we then this weights, when the new data come in, these weights, these weights then finally giving you a y value on which we apply a sigmoid function, and that from that it gives you the threshold value. Now this is the idea behind the activation function. So guys, so this was the introduction to the activation function. Now we have different activation function. So on your screen now, we have activation function that is a sigmoid activation function. And your sigmoid activation is such that, it plots your curve into like this. And now you can apply your threshold 0.5 and you can make a decision, and this is also a threshold that you play, right? And we have various type of sigmoid function. You can go on the slide deck and it will take you to the link where, you can actually play. And we have different kind of sigmoid function. I will talk about this in the next lecture or the next 7.2 part of this entire lecture series. Now, the idea of the activation function is to bring everything on one scale, and it is applied both in the internal hidden layer and also in the output layer. Now, in the internal hidden layer, we apply something called ReLU, but because you're doing here a classification task, I am applying here and I am using sigmoid function, right? Okay. Now, guys, this was the idea. I hope this is clear to you, right? Again, one small thing. Your 0.23, 0 minus 0.53, 0.47 are the weights that are coming from your initial data when you are trying to find the relationship between your independent parameter and your independent parameter and final y. These are the weights that are coming, the relationship between independent parameter and the final y. And these independent relationship gives you these weights which are added. And here, because we had 3 independent parameters, all these 3 things were added together to form a final y that would work inside the neuron. And this equation now can be used for the new data coming in. And this equation now, we are using it for the new data coming in to get these values of y. And all these value of y, to make a crisp decision, here we are doing a binary classification task. It goes inside your sigmoid function. And so that your data start following this trend, and now you can apply your threshold to make a decision. And this is happening in the output layer here. In the input layer, what we have is also the activation function, but the activation function is more linear, because we do not want, that is, we'll talk about something called ReLU in the next, case. And here we have sigmoid, such that, here we do not want your data to be converted into this S feature, right? We just want our data to be linear, and doesn't lose any, doesn't get transformed into any such data, because we're not making decision yet. Decision is made at the last step. I hope this made sense, guys. And let us now quickly dive into what are the types of activation functions.